Hello. In this lecture we will dive a little bit deeper into the authentication process. IKEv version 2 uses one of three methods to authenticate the peer. It can use pre-shared keys, certificates or signatures, as well as using extensible authentication protocol. In the previous lecture, we saw how the keys are generated. The keys that were produced by the two sides included the authentication, encryption, phase 2 keys as well as key confirmation key. The key confirmation key is the SKPI and SKPR. The nice thing about IKEv version 2 is that the authentication method doesn't need to match. Meaning that one side can authenticate using pre-shared keys and the other side using certificates. Okay, there are the concepts of signed octets. The signed octets is crafted by gathering bits and pieces of the two initial IKEv2 init messages. Basically, the initiator gets authenticated by gathering the IKEv header from message 1. It will append it to the rest of the message and produce real message 1. If we see here in this packet capture image, it is composed of the initiator SPI, responder SPI and so on. It will then gather the rest of the initialization payload. It will create a message authentication code using the SKPI, ran against the SA init payload. So, the message authentication code uses SKPI for its key. Now, it will basically line up the signed octets which is composed of real message 1. Meaning real IKEv header concatenated with the rest of message 1. It will concatenate the nonce for the responder which is nonce R. It will then concatenate the message authentication code of the initiator. So, this string of octets is referred to as the signed octets. The responder authentication is also composed by gathering bits and pieces of message 2. It will take the IKEv header and the rest of the message. It will then take the rest of message 2. Using ASCII PR, it will produce the message authentication code of the responder ID payload. It will create the responder signed octets. This is composed of real message 2 concatenated with nonce initiator data, and the message authentication code for the responder ID payload. This is signed octets responder. Now, if pre-shared authentication is in use, what will happen is a bit of pseudo-random function magic again. It will take the pre-shared key, it will then use that pre-shared key in a pseudo-random function of literally, the phrase keypad for IKEv2. So, technically, the pre-shared key does not get communicated directly, it is actually the phrase keypad for IKEv2, hashed with the pre-shared key. The reason why IKEv version 2 did this, is that they didn't want the hash of pre-shared key to be used. Pre-shared keys are considered insecure. If they have used the pre-shared key, an eavesdropper can figure out what it is, by running it against a known hashes list. If they were to use the key itself as is, it would have been easy to deduce that key from the IKEv exchange. So, instead they used the hash of the phrase keypad for IKEv version 2, using the pre-shared key phrase. Then each side takes the signed octets and then hash it with the key which is the outcome of that operation. So if we symbolize the outcome of pseudo-random function of the phrase IKEv2 payload, against the pre-shared key as A, and the signed octets as B. The authentication is the outcome of pseudo-random function of the phrase keypad for IKEv2, hashed using the pre-shared key, and that is used as a key to hash the signed octets. So, it is really complicated for anyone eavesdropping into the conversation to guess the pre-shared key. The pre-shared key can be up to 64 octets, per the RFC of IKEv version 2. Both sides have all the information to run the same auth function, and authenticate the other side. Hopefully, the information was helpful. We will discuss more in the next lecture.